define formally open and closed sets in the context of metric spaces, right? So yeah, this is these notions of open and closed we have already been using in this course, right? Loosely, without much of a formal definition. So in particular, recall that in the set of reals, right, within the set of reals, we have been referring to sets of this form as open intervals, right, and sets of this form as closed intervals. Right. However, at no point have we really formally defined, what it means for a set to be open and what it means for a set to be closed. Right. So the goal of this lecture is to basically define formally what open and closed sets are, but not just in the restricted set of the reals, but in a general metric space. Okay. So whatever we talk about today will apply naturally to R, but more generally to any metric space. Okay. So the goal is, as I said, to formally define open and closed sets. Okay, so the setup is as follows. So throughout, assume that S comma D is a metric space. Right, and that E is some subset of S. Okay, so remember S is my set and D is the metric or the distance function defined on that set. Okay, so we begin with a couple of definitions which lead us to the definition of an open set. So for any element x that belongs to E, which is a subset of my space X, we say that that element is interior to E if the following is true. If there exists some positive real number R such that this set is contained in E. So let's interpret what this means. Let's look at what that set is. It's a set of all y such that the distance between x and y is less than r. Okay, so this set of all points which are a distance less than r from y is in fact called a ball, right? For obvious reasons, because for example, in 3D, all points within a certain distance of a certain point would constitute basically a ball centered at that point, right? So in this case, this is in a general metric space, this is in fact how one defines a ball of radius r centered at x. Okay, so going back to the definition, we say that the point x is interior to E if there is some ball of positive radius centered at x contained completely within E. Right, so if there's a ball of some positive radius contained within E, we say that x is an interior point to E. Okay, so as I said, x is interior to E. Alternatively, we also say x is an interior point of E. Okay, so that's another phrase that we will use repeatedly going forward. Alright, so now that we have defined what it means for an element of a set to be an interior point of it or to be interior to it, we can now define the set of all of such points and denote that as the interior of the set E. Right, so that's the next thing we are going to do. The set of all interior points of E is denoted by E naught. Okay, so E naught is the set of, it's clearly a subset of E, right? Because only points that belong to E could possibly be interior points of E. So E naught is that subset of E which is composed of all interior points of E. And once again, what are interior points of E? These are those points for which there is some ball centered around that point which is completely contained within E, right? So in that sense, from an English standpoint, it justifies why we call those points interior points, right? Because they are in some sense the interior of E, because there is some neighborhood, there is a ball around that point which is in fact completely contained within E. Okay, so having defined the so this E naught is typically denote of also called the interior of E. Okay, and now with all of this, we are now able to define an open set. So a set E, which is a subset of S, is open if E is equal to E naught, right? In other words, if every element of E is an interior point of E, then we say that the set E is open. So that is, if every element of E is interior to it. Okay, so this is our definition of open sets. So when do we say that a certain subset of a metric space is open? When that set is essentially its own interior. In other words, every element of that set is in fact an interior point. So there is a ball around that point that is contained completely within within that set. Okay, so let's now that the abstract definition is out of the way, let's give a few examples. Okay, so let's start off with examples in R. Right, an interval of this form, or more generally of AB, is open. Right, again you have to convince yourself that whenever you have an interval of this kind, every element of that interval in fact has some ball around it which is contained completely within the interval. This is why a set of this form is in fact open by our definition, right? Similarly, if you look at sets of this form, let's say from -1 to infinity, excluding -1, these sets are also open. Right? Why? Because, well, uh, every point within this, actually, for every point in the set -1 to infinity, you can in fact draw a ball around that point which is completely contained within the same set. In other words, every point is interior. Right? Similarly, the set of all reals itself is open, clearly. And so let me also give one example in Rk. Right, sets of this form, let's say X in Rk, such that, well, I don't need to put dk anymore. This d is, maybe I'll do it. This is just the Euclidean distance that we have talked about already in Rk, right, which makes it a complete metric space. Right, if you have a set of this kind, which is what, it's a ball centered at X of radius r. So more specifically, this is the set of all points in Rk which are at a distance of strictly less than r from x naught, right? It turns out this set is also open. Right, sets of this kind we have already in fact used in our definition of openness, right? Because we used sets like these to talk about interior points. So this, now that we know that this set is open, I leave it to you to justify that this is in fact the case. But these are balls of this kind are also called open balls. So this is an open ball of radius r centered at x naught. Now I have stated these all as examples uh, to justify that these are indeed all open sets using our definition of openness just above is basically being left as an exercise, right? To showing that these all these four sets that I have written down here is open is something that I'm going to leave to you, right? In particular, to prove the last one, right? That the ball that I have expressed out here is in fact open, you would in fact have to utilize the triangle inequality, right? So all of this is an exercise. So showing these are open is an exercise. Okay, so having now defined open sets and also having given some examples of open sets, now let's actually talk about some implications of the definition of openness. Okay, so once again, for any metric space, the following are true. S and phi is the empty set. These are both open. Right? This is not hard. The whole metric space is bound to be open, right? Because the whole metric space, by definition, every point of the metric space is interior to the metric space. Okay, so clearly S is open. Phi is also open. This is by convention, right? Because how do you define a set to be open if every point of it is an interior point? Now phi has no points, and so, well, kind of as by convention we say that since there are no points, that criteria that all points are interior points is also satisfied by phi. So by convention, if not by definition, we say that the empty set is also open, right? Now come the important parts. An arbitrary union of open sets is open. Right? We talked about arbitrary unions before. So what I'm pointing out here is that if you have any collection of open sets, it may be finite, it may be countable, it may be uncountable. The union of those sets is in fact also going to be open, right? And I claim this is actually an easy consequence of the definition of an open set, right? So again, I leave this to you to verify for yourself. And finally, a finite intersection of open sets is open. Okay, so these are three implications I claim of the definition of an open set in a metric space: that the whole space and the null set are both open. Arbitrary unions of open sets are open, and finite intersections of open sets are open. Okay, so yeah, proving these in fact from the definition is also left as an exercise, not difficult to do, right? And in particular, when you go through the definition of the last statement here, I would like you to explicitly understand, as you are proving the statement, the importance of the finiteness here, right? So once you have, say, infinite intersections of open sets, you're not necessarily guaranteed to get an open set, right? So finite intersections of open sets are open. However, infinite intersections of open sets need not be open, right? So let me write that as a caution. Non-finite intersections of open sets need not be open. Right? You can in fact come up with very simple examples that do this. So I do, let's say, an intersection over the naturals of actually, never mind. What we can do is basically reuse the same example that we did in the previous lecture. So in particular, the intersection over, let's say, the positive reals 0 to infinity of the set minus y to y. So remember, y is a positive real, okay? And for every y, we are interested in the open set from minus y to y, okay? So these are clearly open. I am now constructing an uncountable intersection of these open sets, and in fact you can check that this is in fact null, right? Yeah, if you want one that involves if you want one that involves only a countable intersection, that's also easy. Yeah, that probably was the example I was going for earlier, which is that if you now look at sets of this form, okay, so I'm now doing an intersection over n being natural of the open sets from minus 1 by n to 1 by n. Okay, this also intersection would just be the singleton set 0, and again this is not open. Okay, so these are a couple of examples in fact of infinite intersections of open sets which are in fact not open. So convince yourself also that the set consisting of the singleton set consisting of only 0 is not in fact open in R. Why? Because 0 is not an interior point of this set. There is no neighborhood, there is no ball around 0 that you can construct which is completely contained within this set. Alright, so yeah, so like coming back, what we have been saying is that really from the definition of open sets, there are three important implications that one can draw. The entire space and the null set are open. Arbitrary unions of open sets are open. Finite intersections of open sets are open. Okay. Now, in the context of metric spaces, these three are in fact consequences of the definition of open sets, right? So we'll write that here. These properties are consequences of the definition of open sets in metric spaces. Right? So recall that we have in fact used the distance function or the metric to define open sets, right? However, it is also of interest to define open sets in more general spaces, right? In fact, in more abstract spaces that don't in fact have a metric. In such cases, the same three properties are in fact used as the axioms to define the set of all open sets. In more abstract spaces, right? When I say more abstract spaces, I mean more abstract spaces without a metric or a distance function. The same three statements are used as axioms. To define the collection of open sets. Okay, because in those spaces you don't have a metric like we do in the case of metric spaces. So in fact, you use these three, you have to come up with a collection of sets which satisfy these three properties, and that collection of sets defines the collection of open sets. So this collection of open sets in more general context is also referred to as a topology, right? And the study of such spaces where the collection of open sets is defined such that it satisfies these three axioms, right? Such spaces are referred to as topological spaces. So we are not going to talk about topological spaces in this course. So I'm just throwing this terminology out there so that you are at least familiar of it. So the study of topological spaces is beyond the content, beyond what this course can do. Yeah, this will show up in a second course on analysis. Right? So let me just reiterate what I just said. The reason why I've written these three properties the way I have is to highlight exactly this generality, that these three properties are easy consequences of the definition of open sets in the context of a metric space, but in more general spaces called topological spaces, these three statements are instead used as axioms to define the collection of open sets, right? And that collection of open sets is called a topology, right? So this is just a pointer for later, but it also gives you a reason to understand why we called this chapter metric space topology, right? The reason we call this chapter metric space topology is because we are defining the topology using the metric associated with metric spaces, right? In other words, we are defining open sets, but since we are doing it in the context of metric spaces, I can use the metric that is built in doing so. All right. So yes, so that's it. That's all I had to say about open sets. Having talked about open sets in some detail, now we can talk about closed sets. So the definition of closed sets is fairly straightforward. A set is closed if its complement is open. Okay, so once again, let's do a bunch of examples. If I look at R, then intervals of this form are closed, right? And how do you verify this? Well, just look at the complement of this set and convince yourself that complement is in fact open by our definition, right? That complement has the property that every point in the complement is in fact interior to the complement, right? So therefore this set becomes closed. Similarly, R and phi are also closed, right? Why? Because R and phi are also complements of each other. So R is closed because its complement, i.e. phi, is open, and phi is closed because its complement, that is R, is in fact open, right? So R and phi are in fact, these are in fact both open and closed sets. Right? On the other hand, you can of course have sets which are neither open nor closed. So for example, if you look at a set of this form, which is the interval from 0 to 1 but including 1, right? So this is in fact neither open nor closed. Right? Why is this set not open? Because the point 1 which belongs to the set is in fact not an interior point. Okay? Convince yourself of that fact. And if you now define the complement of this set, you will realize that 0 which belongs to the complement is in fact not interior to the complement. So neither the set nor its complement are open, and therefore neither the set, so the set itself is neither open nor closed. Same is true of its complement. Okay, so here are some examples in R. One can also come up with easy examples in RK. So in RK, like we defined an open ball before, it's also possible to define a closed ball. So a set of the form that dx comma say x naught is less than equal to R, okay, is closed. Right, so this set for good reason is in fact called a closed ball of radius R centered at x naught. Right, again I'm only stating this as an example. I'm leaving it to you to to go back and prove in each of these, what, 3 or 4 examples, that the sets that I have claimed are closed are in fact closed, right? So you would have to basically look at the complement of the closed ball that I have claimed as being closed. Look at the complement of that. What is the complement of that? It's going to be the set of all x such that d of x comma x naught is in fact strictly greater than r, right? And prove that that set is in fact open. Every point of that set is interior to itself. Again, triangle inequality will play a role. And once you have done that, that would show by definition that this set is in fact closed. Okay, so this is my definition of closed sets. And finally, let me make one final observation. Now recall that we mentioned that arbitrary unions of open sets are open and finite intersections of open sets are open. Now closed sets are complements of open sets. So by De Morgan's laws, you can actually say something about closed sets as well. In other words, while you have arbitrary unions of open sets as being open, you will in fact have that arbitrary intersections of closed sets are closed. Of closed sets are closed. Right? So as I said, it follows from applying De Morgan's law to the statement that arbitrary unions of open sets are open, given that closed sets are complements of open sets. Okay, so our closed sets, arbitrary intersections of them are in fact closed, and similarly finite unions of closed sets are closed. Right? This latter statement follows again by applying De Morgan's laws to the statement that finite intersections of open sets are open. Okay, so both of these are in fact a consequence of De Morgan's laws. Okay, so in this lecture what we have done is formally defined open and closed sets in the abstract context of a metric space. We looked at a few examples and a few consequences of the definition of open and closed sets. Right? So we will have more to say about the consequences of these definitions in the following video.